Okay, so if there's kind of no questions, or if you think of some, you can obviously ask later. Like I mentioned before, again, just keep us on pace because of the exam and no lecture last week. I did record 2 lectures on chapter 7, which was chemical reactions, type of reactions, and also moles, grams, and stoichiometry. So if there is no questions, I do want to kind of go over some of the topics that are in those lectures. Is definitely not a substitute for watching those lectures, but I do want to kind of at least kind of in person touch upon some of those things just to make sure, again, everybody's on the same page in terms of a lot of that material, or at least some of that material. So we're going to then talk about, I guess, for a little bit here about chapter 7 type stuff, which again, there's two basically parts to it. Part 1, which basically covers balancing equations and different ways to classify reactions. And part 2 deals with grams to moles, which is a sort of important calculation, and also using those equations to do calculations, which are known as stoichiometry. So a reminder that, we do represent make sure I'm on the page here. Okay. So we do represent a sort of chemical change with a chemical equation. And basically, the chemical equation uses the symbols for all the formulas, and then obviously balancing those equations are really important. So when we look at a chemical equation like N2 plus H2 makes NH3. Oops, gas there. There's a couple of things. Again, a reminder that on the left-hand side of the arrow, these guys are what are known as reactants. And those are your starting materials in a chemical reaction. And on the right-hand side of the arrow, in this case, we just have one, but you could have more than one. Those are what are known as products, which is the result of a chemical reaction that's taking place. Other common things that we do see again in equations, just like I wrote here, are the states of things. So if you see an S next to a formula, that means solid. An L would mean liquid. G would mean gas. And also a very common one that we see a lot is AQ, which means aqueous. And again, that basically means a solution. And again, a reminder that liquid means you just have one thing by itself, like water, and that's it. Something that's aqueous, you take something like water and you put something in it, like say salt, and dissolve it, and you make a solution, and that's an aqueous solution. Other things that we commonly see, sometimes we'll see things written on top of the arrow, things like the delta symbol, which means heat. Sometimes a catalyst will be put up there. A catalyst is something that basically is not a reactant, it's not a product. It is there simply to make that reaction occur faster. It actually does not get used up in the reaction either. So, it is really there for one purpose, which is to facilitate the reaction really occurring faster than it would if it was not present. There's lots of reactions in chemistry that will take place, but they may be really super slow. You might wait all day and all night for it to happen. And sometimes we do add catalysts to it to sort of speed it up, like the experiment, I think maybe this week, which is the gas experiment. You add some MnO2 to it to speed up that reaction. If you don't, you're there all night. When you're in person, you're there all night if you don't add enough of it. So that's there as a catalyst to sort of speed up the reaction. Now, when we use an equation, it should always be balanced. And obviously, what that means is the law of conservation of mass means that, if we started with 4 sulfurs on the left, we should end up with 4 sulfurs on the right, because really the only thing that happens in a chemical reaction is we break apart bonds. So we break apart all the bonds on the reactant side, and we basically rearrange everybody into some new compounds on the product side. And the only thing that really gets involved in these reactions are the electrons. And remember that when we talked about the atom, the one particle that's really important in terms of what the element is are protons. And remember, the proton, which is the atomic number, tells you what element you're dealing with. And if we do not change the protons in a normal chemical reaction, they're not even really involved, then obviously we should always end up with the same elements on both sides of the equation. They may absolutely be in different sort of formulas, but we should, again, if you started with a certain number of nitrogens, should have the same number on the other side. So when we balance equations, we want to balance the equations by changing only the coefficients, as we talked about in the sort of that video. Again, the coefficients are only the numbers that come in front. So those are the only ones that we could change. We never change the subscript here. We never like insert a number between things or anything weird like that. The only thing that you can do is basically change these numbers. When you're done, you should have an equation that has the same number of elements on both sides. And there's really two important things when you're done balancing an equation. All the coefficients need to be whole numbers. And they do need to be the simplest set of whole numbers. So for example, if we were able to balance an equation, 2a plus 4b goes to 6c, and we'll pretend this is all completely balanced with the right number of elements on both sides. When we look at the coefficients, we actually could go through and divide everybody by 2 to give us a plus 2b gives us 3c. And that would represent really the correctly balanced equation that we would want to do. And sometimes that happens because people could see sort of larger numbers, some people could see smaller numbers. So if you see that you could go through every single coefficient and reduce it down by a common number and still have all whole numbers, you absolutely could do that, and you should do that for it to be properly balanced. Now, if we look at the one I wrote up there originally, we have N2 plus H2 goes to NH3. A very good way to sort of balance equations is to make like a little table and really just count up what you got on the reactant side and the product side. In this case, on the left-hand side, we have 2 nitrogens. The right-hand side, we have 1. Left-hand side, we have 2 hydrogens. Right-hand side, we have 3. So we can see here that nothing's really balanced. And really the easiest thing probably to fix would be the nitrogens. So to fix that, we would go to the right-hand side and put a 2 in front of the nitrogen. That then gives us 2 nitrogen, and then gives us 2 times 3, which would be 6 hydrogen. So this guy gets distributed to both of these guys. And we can see that we balance the nitrogen, but our hydrogen is still not correct. So now we would go back to the other side, the left-hand side in this case, and we would again put only a coefficient in front, and we put a 3, and that will give us 2 nitrogens, and 3 times 2 here is 6 hydrogen. And this would represent the properly balanced equation with all whole numbers, exact same number of elements on both sides. Any questions on that there? So remember that, if you, a couple of things, if you needed to, let's do, like say C6H14 plus some O2 goes to CO2 plus some water. So why don't you take a second here and balance this and make sure you get the same answer. Okay, let's take a look and see, some approaches here. So again, I highly recommend doing it, making some tables here. Sometimes it sort of gives you direction, sort of, it gives you an idea as to where to maybe begin, where to go. So in this case, we have basically carbon, hydrogen, and oxygen, left-hand side, reactant side, product side. In terms of carbon, we got 6 on the left, we got 1 on the right. In terms of hydrogen, we got 14 on the left and 2 on the right. Oxygen on the left, there are 2. Oxygen on the right, there's 2 there, plus 1 more there, gives us 3. So not much here balanced. So, perhaps the easiest move would be to take care of the carbon. And we could simply do that by putting a 6 on the carbon on the right. That now gives us 6 carbons. We still have 2 hydrogens. Oxygen, we're now up to 12 here in the first one and 1 more here in the second. That now gets us 13 in terms of oxygen. We've now fixed the carbon. We're still off in terms of hydrogen and oxygen. Hydrogen probably would be the next best thing to work at, as we do see oxygen in a couple of things over here, but hydrogen's only in 1. So we could fix the hydrogen by putting a 7 in front of the water. And when we do that, again, we still have 6 for the carbon. 7 times 2, again, distributing that gets us 14 for the hydrogen. Oxygen, we're still 12 here, but as we distribute the 7 here, that now becomes a 7, and now we have 19. At this point, we clearly have put numbers on the right-hand side where oxygen is. We don't want to change those numbers, otherwise we're never going to balance this thing. So really the only thing we could do now is to come to the left-hand side, and we want to balance it. So we basically need 19 oxygens, and we only have 2 on the left-hand side. So remember that when you watch that video, as I mentioned, you can absolutely use a fraction in balancing the equation. And the fraction is a very simple formula. The number on top is the number you need. So in our case, we need 19. The number on the bottom will match this number, which would be 2. And if we look at what we just did to the left-hand side, we have 6 carbons still. We still have 14 hydrogens. And when you take, go here, 19 over 2 times 2 from the 2 that's there, the 2's cancel, and you end up with 19 oxygens. First off, any questions on that right there? Now, technically speaking, this equation is balanced, but we cannot leave it like this, because if you remember, basically when you are balanced, you need to make sure that everybody is a whole number in the equation. And in this case, 19 over 2 is not a whole number, so you can't have a decimal or anything like that. So we do need to clear the fraction. And again, we would clear the fraction by multiplying the entire equation by the denominator. And if we do that, we will end up with 2C6H14 plus 19 halves times 2 is 19, gives us 12 CO2 plus 14 H2O. Again, distributing that 2 across the entire equation, basically to everybody. And at this point, we should be balanced. We could triple check here. 2 times 6 for the carbon is 12. 12 on the other side, so that's good. Hydrogen, 2 times 14 is 28. Hydrogen over here, 14 times 2 is 28. And lastly, 19 times 2 is like 38. Over here, we have 12 times 2, which is 24 oxygens, and 14 is 38. So we are balanced here. So again, this illustrates what we talked about sort of in that video. You could absolutely use a fraction to balance an equation, but you do need to clear it in order to have a properly balanced equation. It oftentimes happens like we see here, where you have one element in a couple of formulas on one side and kind of the natural version of that element by itself on the other side, like we have O2. Any questions again on balancing equations here? So another sort of important aspect out of chapter 7 there that I want to kind of touch upon here in discussion is the idea of two or so really important conversions that we use, and that is the idea of Avogadros number and Avogadros number is a natural number. It is 6.022 times 10 to the 23 equals 1 mole. And a mole abbreviation is MOL. And the units associated with Avogadros number can vary. They can be particles if you're talking about particles. They could be atoms if you're talking about atoms. They could be molecules if you're talking about molecules, and so forth. So atoms and molecules are very common uses of Avogadros number. And really, we use it as a conversion factor to go from atoms, our molecules, to moles, and backwards, moles back to atoms or molecules. And we basically set it up like 6.022 times 10 to the 23 atoms per mole, or a mole is 6.022 times 10 to the 23 atoms. So we only really want to use Avogadros number if there's some mention of those words, some mention of atoms, molecules, particles, something like that. So for example, if we had 22.5 moles of sodium, and we want to know how many atoms that would be. The key word here is atoms, which tells us we should use Avogadros number. And we would set it up like a dimensional analysis problem. We would go 22.5 moles of sodium. Remember, we want to get rid of sodium. So moles of sodium would go on the bottom. So we would use the conversion factor here on the left. And we would go 6.022 times 10 to the 23 atoms per mole of sodium. The moles of sodium will cancel, and we would multiply 22.5 times 6.022. We want to make sure, again, we use our exponent button to the 23, and that would tell us we got 1.35 times 10 to the 25 atoms of sodium. Any questions on that there? Now, you don't have to use Avogadros number on just an individual element or atom. We could also use it on like molecules. So for example, if we had 1.25 times 10 to the 22 molecules of NH3, and we want to know how many moles that is. Again, the key here is we see the word molecules, tells us it is Avogadros number time. And again, we would set this up like dimensional analysis, where we would start with that number, which would be 1.25 times 10 to the 22 molecules of NH3. In this particular case, we actually want to get rid of molecules. And that means that we would actually use this conversion factor for Avogadros number. A mole of NH3 would equal 6.022 times 10 to the 23. And in this particular case, because Na3 is not just one atom by itself, it's actually a molecule, the units of Avogadros number will change to molecules. And again, those units will cancel out using our exponent button here, 1.25 to the 22 divided by 6.022 to the 23 gets us a answer of 0.0208 moles of NH3. So Avogadro's number is used again really for that conversion to go from moles to atoms or molecules, or if you are starting with atoms or molecules to go to moles. Again, if there's no mention of any of that stuff in terms of atoms, molecules, or anything like that, you really shouldn't be using Avogadro's number. Any questions on that calculation there? Now, another probably even more important calculation, one that we'll probably use more than using Avogadro's number, is what is referred to as molar mass. And molar mass has units of grams per mole. And we really use the molar mass as also really a conversion factor. And we use it as a conversion factor to go really between two units. We use it to go between grams and moles back to grams. And this is a very sort of important sort of conversion. Where do we get it? We really get the molar mass from the periodic table. And it is when you look at the symbols, it is really the numbers on the bottom. And what we could say about the numbers on the bottom is, for example, in aluminum, if you took 1 mole of aluminum, it would have 26.98 grams. And we would say that the molar mass of aluminum is 26.98 grams per mole. So when you're calculating molar mass, a couple really important things. One thing is the number always stays with the grams part, and it's always per 1 mole. So it's always number with the grams on the bottom or top there is 1 mole. And we really can turn this into two conversion factors. We basically can say there are 26.98 grams per mole of aluminum, or we could flip it around if we needed to, put the mole on top and the 26.98 grams of aluminum there on the bottom. So if we were starting with 425 grams of aluminum and wanted to know how many moles that was, we would start with the 425 grams of aluminum. We would want to get rid of aluminum, which means grams of aluminum, which means we would want to use the conversion factor there on the right, where a mole of aluminum goes up on top, 26.98 grams of it goes on the bottom. The grams of aluminum cancel out, and we end up with 425 divided by 26.98 ends up getting us something like 15.8 moles of aluminum. Any question on that calculation there? Now, to tie this together with Avogadro's number, let's say that we actually wanted to know, in addition to moles, how many atoms of aluminum that would be. At this point, what we could do is use our Avogadro's relationship that there are 6.022 times 10 to the 23 atoms per mole of aluminum, or a mole of aluminum is 6.022 times 10 to the 23 atoms. And we could actually continue on the calculation if we wanted to know again how many atoms that would be. We would want to use a conversion factor here on the left, moles of aluminum on the bottom, 6.022 times 10 to the 23 atoms on top would give us 9.49 times 10 to the 24 atoms of aluminum. Any question on that part of it? So really, when you pull a number off the periodic table, and by the way, when you do pull these numbers off the periodic table, again, that's how many grams there are in 1 mole. And we always go to 4 significant figures in terms of how many numbers that we actually use. But basically, like I said, you could tie both of these together, that 1 mole of aluminum does equal 26.98 grams, and 1 mole of aluminum also equals 6.022 times 10 to the 23 atoms of aluminum. So for anybody on the periodic table, you basically could do that. You could also do molar mass, not with just one element or atom. You could do it with a molecule. So if we had our C6H14, and we were going to want to know how many grams there are in 135 moles of C6H14. So when we look at this problem, we see moles, which is the abbreviation there, MOL, not molecules. No mention of molecules, no mention of atoms, which means we should not use Avogadros number. This again is a conversion between grams and moles, which means we need to go to the periodic table and use the molar mass to do that. So to get the molar mass of this compound, we're basically just going to add up all the parts. So there are 6 carbons, which if you look on carbon on the periodic table, will say 12.01 grams per mole. There are 14 hydrogens, which again, if you look on the periodic table, hydrogen says 1.008 on the bottom, which means that is 1.008 grams per mole. 6 times 12.01 plus 14 times 1.008 gives us a molar mass of this guy of 86.17 grams per mole. Again, we could turn this number, which is the molar mass of this compound, into 2 conversion factors. We could say there's 86.17 grams of this guy per mole. Or we could flip it around and go a mole is 86.17 grams of this guy. Since we're obviously starting with how many grams, we're looking for how many grams. We're starting with moles. To do the calculation, 135 moles of C6H14. We would want to use the one here on the left, as the moles will then cancel and leave us with grams, which would be, in this case, looks like 11633 grams of C6H14. Again, looking at this number, which is 3 significant figures, roughly 11600 grams of C6H14. Any questions on where any of the numbers came from, why I'm doing these calculations? This calculation going from grams to moles or moles to grams is used a lot in chemistry. And again, from the periodic table is basically where we get that conversion factor to do that. A tie-in here, just to tie it in with Avogadros number, we would say that there are 86.17 grams of C6H14 in 1 mole of C6H14, and 1 mole of C6H14 would equal Avogadros number 6.022 times 10 to the 23. And again, these would be molecules of C6H14. Any questions on grams to moles, moles to grams? Now, sometimes when you're doing a calculation, so for example, if we looked at, we just saw there, where'd it go? Steal this one. Let's say we had, let's pick it up from there. Let's say we had 135 moles of C6H14, and we were actually interested in how many atoms of carbon that would be. Now, sometimes in these problems, they're maybe not interested in the entire formula there, everybody in the formula, but they're just interested in maybe one aspect of it. And we can actually use the formula itself as a conversion factor. So when we look at this formula here, we could say, and look at these numbers here on the bottom as moles. We could say in 1 mole of the entire thing, there would be 6 moles of just carbon. And again, the 6 comes from here. So 1 mole of the entire thing gives us 6 moles of carbon. We could also say in 1 mole of the entire thing here, we would have 14 moles of hydrogen. So sometimes we need to use the actual formula as a conversion factor. And this is a mole to mole sort of conversion, which means we would need this number in moles, which it already is. So we could start with 135 moles of C6H14. Again, we want to get rid of the whole thing and end up with just carbon. And we would end up with 1 mole of the whole thing gives us our 6 moles of carbon. Moles of the whole thing cancel. We're left with moles of carbon, which if you get an answer at this point would be 135 times 6, about 810 moles of just carbon. But moles of carbon is close to what we're looking for. We are looking for atoms. So the key word there is atoms, which means Avogadros number here is what we need to use. 1 mole of carbon would be 6.022 times 10 to the 23 atoms of carbon. The moles will cancel, and we will end up with, looks like something like 4.88 times 10 to the 26 atoms of carbon. So again, occasionally when you're doing some of these sort of grams to moles, moles to grams, so you might be interested in just one part of the formula where you could actually use the formula as an actual conversion factor. Any questions on sort of that calculation there? So to finish up here in this discussion about some of the main parts of chapter 7 here, and again, obviously there's more and you should watch those videos. Putting kind of both of these things together, the balanced equation and sort of grams to moles, we could do what is referred to basically as stoichiometry. And stoichiometry allows us to do calculations to figure out, you know, if we throw into a chemical reaction a certain amount of reactants, how much products we should make. We could also use it to, if we know in a reaction how much products we actually made, we can figure out how much reactants we actually started with. So when we do stoichiometry problems, there's really 4 basic steps that all stoichiometry problems that we do in this class follow. The first thing is you always want to make sure that you start with a balanced equation. None of it works if the equation is not balanced. So 100%, if they give you an equation, there's no numbers in the coefficients, you should definitely look and make sure it's balanced. If you see numbers, it's probably going to be balanced, but you should always double check. Then they typically will give you one piece of information. So whatever they give you, you want to convert that into moles. So it's very common that you are given grams, go to grams to moles, again, as we just talked about, using the molar mass to do so. Once you have it in moles, you go to the balanced equation and you're able to use the balanced equation to find the mole to mole relationship of what you're interested in. And lastly, sometimes you need to convert from moles to some other unit that they want. Again, this is very common that you might have to go from moles to grams on the back end of the calculation. Also, molar mass is something that we use for that. So let's take a look at one here and just sort of go through a one to explain these 4 steps. So let's just say we had an equation. I don't know what equation I want to do. Let's do this. Let's do Cu plus AgNO3 go to CuNO3 2 plus I squeeze it in there, silver. So first off, we want to know if we produce 35.5 grams of silver, how many grams of silver nitrate did we start with? All right, so first things first, we have an equation. I don't see any numbers, so I want to make sure that it is balanced, and looking at it, it is not balanced. So we want to first take care of this step. This actually has a polyatomic ion on the right, which is NO3, and on the left, which is NO3. There are 2 NO3s on the right, only 1 on the left, which means that's a good place to start. We'll put a 2 there. That then gives me 2 silvers, which I could put the 2 there. And now have 2 silvers, 2 nitrates, and 1 copper. We are now balanced in this case. The next thing that we want to do is take whatever they gave us and convert it into moles. In this particular case, the only thing they gave us was that we have produced 35.5 grams of silver. So step number 2 is we would want to take that 35.5 grams of silver and convert it into moles. That will require us in this particular case to go to the periodic table and find silver. And if you do, you will see a box that looks something like this with like 107.9 on the bottom. And again, what that number represents is that there is 107.9 grams of silver in a mole, or a mole is 107.9 grams. So we're going to use it as a conversion factor. We have grams up on top. We want grams on the bottom, which means we need to use the guy on the right. That would be 107.9 grams of silver per mole of silver. That is going to convert what they gave us from units of grams to units of moles, which is what we need. And in this particular case, we end up with, we'll call it 0.329008. We'll go take it a few digits here. Moles of silver. First off, any questions on that calculation? That's essentially what we were just talking about, going from grams to moles. This right here, if I could find my thing here, there it is. This right here is the molar mass from the periodic table. The reason we really do need to convert these things into moles is because for step number 3, and step number 3 is the big stoichiometry part of the step or the calculation here, and what people sometimes get freaked out about. And a reminder again, if you watch the videos You will understand this. And if you didn't, again, I would recommend you definitely do. We could go to the balanced equation, which is why it's really important to use a balanced equation. And for each of those coefficients, we could say that those are the moles of what we see. So again, we don't write one, but that's one and that's one. And we could say for every 1 mole of copper, we would also put in there 2 moles of silver nitrate. They are equal to each other, not in the sense, again, that 1 equals 2, but they're equal to each other in the sense of proportion. Like for every 1 mole of copper I throw in there, I got to put in there 2 moles of silver nitrate. We could do that for everybody that's here in this equation. We could say 1 mole of copper gives us, right out of room, we'll go on the bottom here, 1 mole of the copper 2 nitrate. We could also say for every 2 moles of silver nitrate, it gives us 2 moles of silver. Every 2 moles of silver nitrate, 1 mole of copper 2 nitrate, and so forth for all those relationships. For each of these equalities, we can write 2 conversion factors to use in the calculation. So when we get to step number 3, really what we're looking at is the 2 things we're interested in. And one thing we're interested in is what they gave us, which was the silver. And the other thing we're interested in is what we're looking to find, which is the silver nitrate, I believe in this case. And from that equation, we could find the relationship, and it's nothing more than the actual coefficients in the balance equation. For every 2 moles of silver nitrate, we get 2 moles of silver. And from this, we could write 2 conversion factors, 2 moles of silver nitrate, 2 moles of silver are 2 moles of silver over 2 moles of silver nitrate. Again, you will not use all of these conversion factors in one problem. You just want to use the appropriate one. And the appropriate one would be determined by our previous step. So looking at our previous number that we got, which is this guy, we would take 0.329008 moles of silver. And this is the big stoichiometry part. We want to get rid of silver and end up with the silver nitrate, which means that is the conversion factor we want to use. 2 moles of silver nitrate from the equation, and we get out 2 moles of silver. The moles of silver cancel. And again, that relationship comes from the coefficients in the balanced equation. And that is the stoichiometry part. And that is what allows us to go from just silver to silver nitrate, which would in this case be the same number when we do it. Any questions on that there? Now we're close to what we want. This is moles of silver nitrate, but we're actually looking for grams. So we do need to do step number 4, which is to convert the moles where we're at now into grams. So we have 0.329008 moles of silver nitrate. In order to go from moles to grams, we need the molar mass. So silver is 107.9, nitrogen is 14.01, and oxygen is 16, which means if we calculate the molar mass of silver nitrate, it would be 107.9 grams per mole for the silver, plus 1401 grams per mole for the nitrogen, plus 3 times 16 grams per mole for the oxygen. And basically adding up all the parts. So 3 times 16 plus 14.01 plus 107.9 gives us a molar mass of 169.9 grams per mole. Remember, we're going to use this as a conversion factor here. And in this case, we want the moles on the bottom. And remember, molar mass is only 1 mole. The number stays with the grams part. And if we do that, we end up with, looks like 55.9 grams of silver nitrate would be needed to be added to that equation. And again, those are the 4 basic steps for a stoichiometry problem. You basically just do these 4 steps in a row. If something's done for you, you just skip ahead to the next step. What that number basically represents is if we did this reaction and we put in there 55.9 grams of silver nitrate. So we started with 55.9 grams of this guy. What we should get out in terms of silver as our product would be the 35.5 grams of silver would be produced. So all stoichiometry problems that we deal with basically follow these same 4 steps. Again, don't undo steps, don't go backwards, but if something is done for you, just go forward. And you could do it all in parts like I did here, all the 4 steps sort of in parts, or you could do all 4 steps together in one big calculation. They all should relatively give you the same idea. Sort of question on the quick version here of stoichiometry. Any questions on anything we talked about here tonight? Again, these are some of the highlights or lowlights, I guess, depending on your perspective of chapter 7. And again, the stuff we talked about here towards the end would be in the second part of the lecture. The balancing equations and types of reactions would be the first part. You are responsible again for both parts. So again, make sure you watch it. Maybe next week we'll do a little bit more